State transition diagram for a pipeline unit based on single-electron tunneling. Abstract: for low cost, low power consumption, high operating speed, and high integration density-based electronic goods are economically indispensable in business, engineering, science, and technology in the present era. Single-electron tunneling is one such approach by which all the logic gates can be implemented. Single-electron tunneling devices, SEDs, and linear threshold gates, LTGs, have the capabilities of controlling the transport of only an electron through a tunnel junction. A single electron which has the charge sufficient to store information in a SED in the atmosphere of 0 K. Power being consumed in the single electron tunneling circuits is very low comparing the CMOS circuits. The speed of the processing of LTG-based device will be very close to electronic speed. The single electron transistor, SED, and LTG both attract the scientists, technologists, and researchers to design and implement their large-scale circuits for small cost of the ultra-low power and its small size. All the tunneling events in the case of a LTG-based circuit happen when only a single electron tunnels from one conductor to other through the tunnel junction under the proper applied bias voltage and multiple input voltages. For implementing a state transition diagram for a pipeline unit, LTG would be a best candidate to fulfill the necessities requiring for its implementation. As far as ultra-low noise is concerned, LTG-based circuit would be a best selection for implementing the desired tunneling circuits. Different LTGs, a D flip-flop, a 2:1 multiplexer are implemented, and above all, a state transition circuit for a pipeline is implemented also. Keywords: state transition, electron tunneling, Coulomb blockade, pipeline, linear threshold gate. 1. Introduction. We are interested in constructing a state transition diagram for a pipeline unit which can provide us with collision or collision-free transition for latency m. M is an integer number. Our intention for doing so is to utilize the electron tunneling phenomena through the SED as there is very ultra-low power being consumed for a single electron while tunneling. For the purpose of the implementing of a state transition diagram circuit, one can take advantages of SED and other one can take that of LTG. In the present situation we will accept the second case, i.e. using LTG a state transition diagram will be presented. The logic gates required to construct state transition diagram for a pipeline unit are being OR, N, NAND. In addition to them, I, combinational circuits like 2:1 multiplexers and 2, sequential circuits like D flip-flops will be necessary. All of them will be described step by step and their comparative studies will be shown in due places. 2. Tunnel junction and single electron transistor. A tunnel junction is made up of two conducting materials and a thin insulating barrier between them. The tunnel junction must have a capacitance C and a resistance. The conducting electrodes of the tunnel junction will be a superconducting or semiconducting material. When we are considering them as superconducting, electron, S, having one elementary charge, 1.60217662 times 10 to 19 coulombs, carry the current through the junction. We have the knowledge that current can't flow through the insulating barrier as it creates a barrier against the movement of an electron in the case of classical electrodynamics, whereas for the case of quantum mechanics, there must be a positive possibility that when an electron residing in one side of the barrier of the insulator in order to reach the another side of it, the electron to which the bias or input voltages are supplied can go to the other electrode. If bias voltage greater than the threshold voltage is applied properly, there will be a current flow. Avoiding other effects, the current will be following in proportion to the bias voltage applied as per the first order approximation tunneling process. In electrical terms, a tunnel junction, of course, have a constant resistance R value relying on its barrier thickness as shown in Fig 1a. When the two conducting materials are connected with an insulating layer between them together, there will also have a capacitance in the junction. In this context, the insulator represents itself as dielectric and two conducting plates with dielectric forms a capacitor C in the tunnel junction. For the discrete nature of electric charge in the tunneling phenomenon, current following through a tunnel junction is discontinuous, i.e., a series of events in which merely one electron will be able to pass or tunnel through the tunnel junction at a particular time. Owing to the single electron tunneling through the junction, the tunnel capacitance is charged with an elementary charge, 1.60217662 times 10 to 19 coulombs, developed a voltage according to the relation equals, where C equals tunnel junction capacitance. When the capacitance of the tunnel junction is ultra-small in order of 10 to 18, the voltage building up in the tunnel junction will be adequate to prevent another electron, S, to tunnel through. We will be able to suppress electrical current when the bias voltage being applied is lower than the voltage created in the tunnel junction. As a result, the resistance of the device will no longer remain constant. The increment of the differential resistance of the tunnel junction around zero bias is said to be the Coulomb blockade 1, 10, 13, 15. The principle of single-electron technology 1, 2, 3, 4, 8 is developed on the basis of the single-electron tunneling events as well as Coulomb blockade. Single-electron tunneling circuits can be taken as a promising candidate for future VLSI circuits for its ultra-low power consumption, ultra-small size, reducing node capability, high integration density and rich functionality. A set 2, 3, 5 made up of two tunnel junctions 1, 2 and having their capacitances 1 and 2 with their resistances 1 and 2 respectively, two other capacitors and 1 are shown in Fig 1, b. They shares only a common inland bearing a low capacitance. The electric potential of the island can be tuned in, i.e., increased or decreased, by a third electrode, called gate, and the gate is being coupled to the island through a capacitor. An extra capacitance, one which is intentionally connected to the island for the purpose of manipulating the gate voltage, input. The drain, source, and gate voltages may be marked by and, respectively. For proper operations of a set, both of the resistances 1 and 2 should be greater than, equals H/225.8 kΩ and charging energy EC equals E2/2C where equals 1 plus 2 plus 1 should necessarily be greater than thermal fluctuations, I.E, equals 22, the product of the Boltzmann constant, K, 1.380649 times 10-23 Joule/K, and the temperature, T in Kelvin. 3. An inverter N symbol. For a stable operation and output, an inverter is unavoidable for the logic gate family of TLG, and this is why we have described the architecture and the arrangement of its different components. The inverter 1, 7 is made up of two sets connected in series as depicted in Fig 2a. Two input voltages, of the same values are directly coupled to the islands of the SET1 and SET2 through two physical capacitances 1 and 2 respectively. The island of each of the SET1 and SET2 has a size smaller than 10 nm of gold and their capacitances should be less than 10 to 17 F. The output terminal 0 is directly connected to the common channel of the two sets and to the ground via a capacitor. To put down charging effects, the operation of the inverter can be described like this: when the bias voltage is properly applied, the output 0 of the inverter will be high, logical 1, when the input voltage is low and 0 value will be low, logical 0, when the input voltage is high. How does it happen? We set the voltages, 1 equals 0, 2 equals 16 MV along with the tuning gate voltages, at present, both for SET1 and SET2. Now if is logical 0, the SET1 is in conduction mode and the SET2 is in Coulomb blockade. This results the output being connected to bias voltage and causes the output voltage to be high. Coulomb blockade works against the steady flow of current because as soon as the high voltage, logic 1, is applied to the input, it causes to shift the induced charge on each of the islands of the two sets by a fraction of the charge of an electron and keeps the SET1 in Coulomb blockade and the SET2 in conducting mode. Eventually, the output changes from high to low. For the inverter, the parameters values chosen for the simulation are 1 equals 0, 2 equals 0.1 times, equals 9. If the threshold dot equals 2, I being an integer value, this implies that the gates perform their functions correctly for any value in the range -1 equals. For the purpose of maximizing robustness for variations in parameter values, the threshold value equals can be replaced by the average equals 0.5. As a result, we will be able to express the threshold logic equations for the two input AND or NAND and NOR gates as below. The threshold gate-based implementations of the Boolean logic gates have the same basic circuit topology will be drawn in the subsequent sections. The threshold gates consist of a bias capacitance, a tunnel junction capacitance, and an output capacitance 0 and they are connected in series. The AND and OR gates contain two input capacitors C1p, C2p. For both the AND gates, the two input capacitances are C1p equals C2p equals 0.5. For positively weighted inputs. On the contrary, for the NAND and NOR gates, two capacitors bearing the value C1n equals C2n equals 0.5. For negatively weighted inputs, each threshold gates is augmented with an inverter/buffer for stable output. The logic function done by the buffered threshold gate is being the complement of which is done by the threshold gate itself. For instance, a buffered gate implements the function For the rest of our discussion, when we are referring to a logic function such as n, we enforce that the logic function totally performed by the entire gate, i.e., threshold gate plus an output buffer. The parameters used for the constructing elements and simulations of different gates like n, or, NAND n, NOR gates and other combinational or sequential circuits are given in Table 16,7. 5 OR gate. To implement a state transition pipeline circuit, some logic gates are essential. One of them is an OR gate. For implementing the OR gate we shall use the parameters 1 equals 2 equals 0.5 AF 3 equals 11.7, equals 4.25, comma, 1 equals 2 equals 0.5, comma, equals 9, comma 0 equals 8, comma, equals 1050, equals 16. In Fig. 4a, and accordingly after running the simulator the output we get is given in Fig. 4b. 6 AND gate. Another logic gate named AND gate is invariantly required to implement the state transition pipeline circuit unit. For the purpose of implementing the AND gate we need to use the parameters 1 equals 2 equals 0.5 AF, equals 4.25, comma, 1 equals 2 equals 0.5, equals 9, comma 3 equals 10.6, 0 equals 8, comma, equals 1050 in Fig. 5a, and accordingly after running the simulator the output we get is given in Fig. 5b. 7 NAND gate. One universal logic gate categorically named as NAND gate must be required to implement desired state transition pipeline circuit in this paper. To implement the NAND gate, we will use the parameters 1 equals 2 equals 0.5 AF, equals 4.25, comma, 1 equals 2 equals 0.5, equals 3 equals 13.2, comma, equals 9, comma 0 equals 8, comma, equals 150 in Fig. 6a, and accordingly after running the simulator the output we get is given in Fig. 6b. 8 Design of D flip-flop using logic gate. The flip-flop is a sequential circuit used for storing information with the help of two stable states, either 0 state or 1 state. To construct a shift register, one type of flip-flop, a D flip-flop, will be needed. A classical D flip-flop is made up of 4 NAND gates and 1 inverter shown in Fig. 7a. There are 2 inputs D input and clock signal input, and 2 outputs Q and Q. The input-output relationship of the D flip-flop is shown in the Table 2. The pattern of the D flip-flop drawn in Fig. 7a will be necessary in the case of implementing a D flip-flop with the help of LTG-based NAND and a buffer/inverter shown in Fig. 2a, or 2c. The same parameters indicated for the case of a NAND and an inverter will also be used in the LTG-based D flip-flop. The output is provided with the positive edged trigger of the clock pulses. The implemented D flip-flop required for our desired state transition pipeline circuit unit is depicted in Fig. 8a. The Fig. 8a, given below is a D flip-flop implemented by LTG logic gates and its input and output signals shown in the Fig. 8b through 8e, are the D flip-flop input signal, clock signal, output of the Q and output of Q respectively. 9 2x1 multiplexer. A multiplexer is a selection or control circuit that selects one input from many inputs with the assistance of control line, S. The simplest multiplexer is a 2:1 multiplexer which is drawn on the basis of LTG-based N and OR gates. The input-output simulation relationships of a 2:1 multiplexer are being depicted in Fig. 9b through 9e. This multiplexer needs to be made for our state transition circuit. 10 A dynamic pipeline and its reservation table. The feedback and feed-forward connections shown in the Fig. 10a make the scheduling of successive events into the pipeline a non-trivial task. By this connection we can take output not only from the last stage but can take from other stages also. From the different data flow patterns, we can use the same pipeline for evaluating different functions like x and y. C:\users\Anup Kumar Biswas /desktop /3stage pipeline.png. Fig. 10a, a dynamic pipeline. The pipeline is really very interesting as nonlinear patterns are being followed there. A static pipeline is specified by a single reservation table whereas a dynamic pipeline can be specified by more than one reservation table. 17. Two reservation tables for the dynamic pipeline are drawn in Fig. 10b and 10c, corresponding to a function x and a function y. Fig. 10c, reservation table for function x. Two state diagrams we have obtained from the two reservation tables are given in Fig. 10d and 10e. A state diagram is obtained for the reservation table in Fig. 10c, by using a 7-bit shift resistor, and another state diagram can be obtained for the reservation table given in Fig 10b, by using a 4-bit shift resistor. The process of making state transition diagram is given in sections 13 and 14. 11 Terminologies of latency analysis. I. Collision. Number of time units or clock cycles necessary between two initiations for a pipeline is considered as the between the initiations. The value of the latency is a non-negative integer number. A latency of p indicates that two initiations are separated by p clock cycles associated with the same reservation table. Any attempts by two or more initiations to use the same stage, like, of the pipeline at the same time will make a 2. Forbidden latencies. A collision implies that happening between two initiations in the same pipeline. Alert is necessary so that all collisions can be avoided in scheduling a sequence of pipeline initiations. Some of the latencies causes collisions but some doesn't. Latencies which are responsible for causing collisions are called. Noted that to detect a forbidden latency, we need to investigate the distance between any two check marks in a row of the reservation table. For example, in the first row, stage 1, of the reservation table in Fig. 10, see, the distances between column 1 and 6, between column 6 and 8 are 5 and 2 respectively, so the latencies 5 and 2 are forbidden. 12 Collision-free scheduling steps. A transparent method for identifying collision-free latencies finds out the possible issue sequences, and this will be presented in this section. These sequences are termed as. This transparent method is discussed in the following 4 steps. Step 1. We compile a list of issue latencies responsible for causing collisions in each row of the reservation table. To do this, an example with a reservation table is given in Fig. 11. We must investigate the column distances between any two cross marks, times, in the same row. In stage 1, first row, of the reservation table having column distance between two cross marks, times, equals to, 9-1, equals 8. So, there is a collision within, equals 8. The latencies causing the collisions are presented below. 2. Step 2, from the reservation table, forbidden list are collected by taking the set of all non-zero row forbidden latencies. So the forbidden list is equals, 1, 5, 6, 8. This list informs us that new issues can be constructed without collisions for the latencies of 2, 3, 5, 7, 9 plus. It is noted that plus indicates any latency greater than that number considered. 9 plus means the integer number 9 and the integer numbers greater than 9. 3. Step 3, for the case of initial state, a collision vector is made up of the forbidden list. The vector is read from the right to left by using 1 for collision and 0 for collision free. Noted that the last non-forbidden latency of 9 is avoided in the collision vector. In the collision vector, the rightmost element is 1 as 1 indicates a collision, 2, 3 and 4 are not in the forbidden state, so we put the 0, 0 and 0 for the positions of second, third and fourth in the collision vector. In the same manner, in positions 5th, 6th and 8th we put 1, 1 and 1. For the 7th position we set 0. 4. Step 4, state transition diagram to be drawn. The collision vector we have got is V equals 1 0 1 1 0 0 0 1. The transitions from the vector are 2, 3, 4, 7 and 9 plus. To get the next state collision vector, the present state collision vector is shifted rightward for each transition. Then the shifted collision vector is ORed with the initial collision vector, as a result we get a new collision state vector. 13 Permissible and forbidden latencies. From the collision vector discussed above we can make a state diagram that specifies the permissible state transitions among successive initiations. The collision vector SAD phase 1, 2 1 corresponds to the initial vector of the pipeline at time 1, and this is why it is said to be an. We assume that P is permissible latency in the range 1, 2, 3, 1 i.e., 1 equals 1. The next state we are considering for the pipeline at time plus is obtained with the help of an m-bit shift register given in the Fig. 13b. The initial collision vector is now stored into the resistor. The resistor is then shifted towards right. Every 1-bit shift towards right corresponds to an increase of the latency by 1. When A0 exits from the right end after P shifts, it indicates that P is A. In the same manner, for A1 being shifted out from the right end tells us A, and thus the corresponding latency will be. For an example, we consider an initial collision vector, 1 0 1 1 0 1 0, and after right shifting the permissible and forbidden latencies are depicted in Fig. 12 below. 14 State diagrams. The Fig. 13, A, and 13, B, are the same logic circuits. First one is made up of CMOS gates and the second one is of LTGs. Initially there is no state stored in the shift register. So the initial value of 1,21 is taken to be 0, 0, 0, 0. When the initial collision vector 1,21 is passed through the OR gates with 0, 0, 0, 0, we get the same output of OR gates as the collision vector is. And this vector is loaded in the shift register if we set equals 0 and apply a positive edge trigger clock pulse. The register is then shifted towards right 1 bit. We know a 1-bit shift represents an increase in the latency by 1. Similarly, a 2-bit shift corresponds to an increase in the latency by 2 and so forth. In this shifting process, when a 0, 0 emerges from the right end, i.e. at the output terminal 1 after shifts, it indicates that is A. In the same way, while a 1, 1 emerging from the right end, i.e. at the output terminal 1 after shifts, it means A. And the corresponding latency P is treated as in the Fig 13, B, if equals 1 and positive triggered clock pulses are applied, the logical zeros enter from the left end of the register and is loaded into the register. What will be the next state after P number of zeros shifting towards right? This is obtained by bitwise ORing the initial collision vector 1,21 with the shifted register contents. For instance, the initial collision vector we assume to be equals 10111010, and which will really be the shift register's contents. After one right shift, the contents of the shift register will be equals 010101. These two vectors are bitwise ORed and we have the next state 11111111. After 2 shift, 4 shift, 5 shift, 7 shift there will be collision states. With the help of diagram, drawn in the Fig 13, B, as well as Fig 13, A, we will be able to explain the creation of initial and new state diagram. Taking n equals 8 in the general initial collision vector V equals 1,21, we have from reservation table in Fig 11. These two vectors are bitwise ORed by the topmost level OR gate circuits in Fig. 13, B, and we get the same values as vector V equals 10110001. The 3 input terminals in the left-hand side for Fig. 13, B, are 0 input, and clock signal. If we set 0 in the terminal, then all the second-level circuits which are 2:1 multiplexers select the outputs of all the OR gates, not select the 0 input. The outputs of all the 2:1 multiplexers are being present at input terminals of all the D flip-flops. At this time we apply first positive clock and all the data present at the input side of D flip-flops will enter into the flip-flops and their output will be D equals 876543321, equals 10110001. Next step, if we set 1 in the terminal, then the 0 is selected by the leftmost 2:1 multiplexer and other multiplexers, from second left to rightmost one, will select the values from 8765432, equals 10110000. Now if a clock pulse is applied, the output of the register will be 01011000, i.e. one right shift happens. This shifted vector is automatically ORed with the initial collision vector. Depending upon the value of the transition, we apply the clock pulses and get the required state transition from the output of the OR gates. We can take 2 right shift as there is 1 out transition equals 2. So after setting equals 1, 2 clock pulses are applied to get the new transition state 2 from the OR gates. We can repeat the process for the transitions 3, 4, 7, and 9 plus. For the case of out transition 3, we apply another clock pulse and take the output from OR gates and get 3. In the same way for the next transition 4, 7, and 9 plus, we apply the clock 4, 7, 9, and more pulses and obtain the next state transitions 4, 7, 9 plus respectively from OR gates. As we have obtained all the next transition states, we are ready to draw an initial state transition diagram, STD, Fig. 13, C, based on these next transition states I.E, 3, 4, 7 and 9 plus. Fig. 13, C, an initial state diagram. With the help of the Fig. 13, B, and the next state transitions 2, 3, 4, 7, 9 plus, we can find all the new transition states and can draw the complete transition state diagram as shown in Fig. 13, D. Fig. 13, D, complete transition state diagram. 15. Discussion. We are interested in determining the processing delay of any logic gates, combinational and sequential circuits based on the LTG gates. To find out the delay of a logic gate we must involve critical voltage, given in equations 6 and 7, as well as the tunnel junction capacitance. However, we assume at t equals 0k, the switching/processing delay of a logic gate can be calculated using the approach 7, 8. The slowest switching happens whenever the critical voltage has the value lesser than the tunnel junction voltage, i.e., but very close to it. This must happen, for example, when only 1 is logic 1, resulting, equals 11.8 MV for the case of a 2-input NOR gate, the critical voltage of the tunnel junction voltage is 11.58 MV. It is considered that the probability of error change, equals 10-12, equals 1050. We obtain a gate delay equal to 0.07281 ln. Ns equals 1.675 ns. In the same manner, we are capable of calculating the circuit delays written in Table 2. When a charge tunnels through the tunnel junction, the amount of total energy in the circuit changes before and after the tunneling. So the difference between the energies before and after the tunneling event is calculated by the relation equals 18. And it is the amount of switching energy consumed when a tunnel event occurs in the tunneling circuit. We have drawn curves regarding the switching delay as a function of the switching error probability in Fig 14a, and the switching delay as a function of the unit capacitance C, which is shown in Fig 14b. Fig 14a, delay versus error probability. C:\users /Anup Kumar Biswas /desktop /delat vs capacitance.png. Fig 14b, delay vs capacitance. We have found out the area/element numbers for every case of gates, its switching delay, and switching energy consumption for the corresponding individual linear threshold gate, using the same methodology as adopted for the Boolean gates. The switching power versus area/element diagram regarding our present LTG-based circuits is shown in Fig 15. Next, we have calculated those parameters for state transition circuits and that are presented in Table 2. In the Fig. 13b, time delays for the phase 1 is 0.340 ln, ns, for phase 2 is 0.5 ln, ns, for phase 3 is 0.66 ln, ns, for phase 4 is 0.82 ln, ns, and for phase n is 0.340 plus 0.160 times 1 ln ns. With the assistance of the data taken from Table 2, the processing/switching delay of a state transition diagram of a pipeline unit having phases n is 0.340 plus 0.160 times 1 ln ns. We have discussed about collision vector above having number of vector elements equal to 8. Given that the value of equals to 10 to 10, so the time after which the 8th bit of the register content will emerge from the pipeline unit is 0.340 plus 0.160 times 8 to 1 ln ns equals 26.13 ns. We are to determine the clock pulse duration, and it is determined by the maximum delay of an OR gate or a 2:1 multiplexer or a D flip-flop. From the Table 2 we are able to get their delays, and the maximum delay of them is C:\users /Anup Kumar Biswas /desktop /power vs elements.png. Fig 15. Switching power versus area/element. Therefore the clock cycle time should be at least 8.887 ns. So the last 8th bit output will emerge after 26.13 ns. If we consider the Fib 13b as a pipeline system, then after every clock pulse of time 8.887 ns one output will emerge from terminal 1 in Fig 13b. If the value of n is a big number, then output rate or frequency of the pipeline will be 16 switching delays of LTG and set. The time delay/processing delay for a CMOS logic gate like NAND, NOR, XOR is 1/2 ns20, whereas the time required for tunneling through a single-electron transistor, SET, is approximately 4 ns4, 5, 16, 18. The XOR gate using conventional logic circuits requires 16 transistors, whereas the same function can be implemented with the help of just one SET. 3, 5, 6, 11, i.e. number of nodes can be reduced to 1 in lieu of 16. Given that error probability is 10 to 15, then the delay for the inverter will be 2.3025 ns, and similarly the other delays for the other gates can be calculated and are shown in Table 3. It is clear that the LTG-based circuit is faster than the SET-based circuit when equals 10-15. The comparison of delays for SET and LTG gate-based circuits is drawn by a bar diagram in Fig. 16. 17. Conclusion. How an electron tunnels through a single electron transistor in an inverter is discussed at first. A generic linear threshold logic gate implementation is elaborately discussed and from which we have been able to derive a family of logic gates like AND, NAND, OR. All the gates along with a 2:1 multiplexer and AD flip-flop have been implemented and are verified by means of simulation using Simon. The number of elements for logic gates, their delays, power consumed by them are given in a tabular form and their related curves or bar diagram are also given in the annexed figures. By dint of all these LTG gates being required as well as an inverter, a pipeline circuit called new collision state creating unit based on LTG having n stages, has been presented. With the help of this pipeline circuit we have been able to draw the state transition diagrams. In single electron tunneling technology, it is observed that the logic gates are at least 3 times faster than CMOS-based logic gates. The atmosphere temperature is kept very close to 0 K in real operation.